Hello everyone and welcome to a video explaining the synthesis component of experiment 4 for Chem 143B. The goal of this video is to kind of appreciate why everything is done in the order that it's done in, because I don't feel like the pre-lab really covers that, and in the case that you do get tested on this, it's something good to know. So without further ado, let's begin. I'm not really going to go over the majority of the background for this, like why you're doing it and whatnot, more of just how to do it and why you should appreciate every step that's taken. Really briefly though, what you're trying to do is make a penicillin derivatives by modulating this R group right here. And what you're doing is you're treating it with an acid chloride to effectively get some form of amide coupling between this nitrogen right here, this nitrogen or amine group with this acyl chloride. Effectively, what you're going to be doing is displacing the chlorine and doing a nucleophilic attack onto that sp2 carbon center. If this is a review for you, it's fine. That's not really the point of the video, but all you should recognize is that these are the two groups that are going to be reacting with one another. So your final product will no longer have an amine, but it should actually have an amide with just effectively this moiety, like this. You'll also be creating a salt of chlorine, but that's besides the point. Anyway, without further ado, let's actually begin into the synthetic process of this to appreciate what's happening. So first and foremost, you have this molecule right here, and it's kind of important to recognize certain features of your molecule before you start doing anything in your synthesis. And one thing I note is that, oh, hey, look, I have a carboxylic acid here. That could cause an issue somewhere in the reaction timeline. So whether it be setting up the reaction, purifying the reaction, or doing the workup. And additionally, I have this free amine right here. And I also have, in general, what is a beta-lactam, which is this four-membered strained ring that contains an amide inside. An amide. And there's a few things to note here. One, this carboxylic acid group is acidic, meaning that it's probably going to be deprotonated in regular water. Its pKa is roughly around 5. I have this amine, but what's interesting about this amine is that it's got some, it's more characteristic of an amine within an amino acid because you have this kind of moiety right here, right? Which is reminiscent of an amino acid. It's not exactly one, obviously, because this isn't an OH, but what you can recognize, though, is that a typical amine's pKa is around 10, but this one is going to be around probably 7, 7.5, 8-ish. And so I already have that listed here for the amine, or the protonated amine, rather. And you also have the pKa 10 of your, or not pKa 10, sorry. That's for the normal protonated amine, and this is for the amine that we're currently working with. The pKa of your carboxylic acid is going to be about 5. And lastly, you have this beta-lactam, which is a four-membered strained ring that is also prone to hydrolysis. And so your solvent actually is water. So this is going to be a big concern with how to deal with things, because if you make a solution too basic or too acidic, what you could also get as a side product is the hydrolyzed beta-lactam. You don't want that to happen, so you have to take pretty good precaution, and I'll explain where this precaution is taken to ensure that you get good product. So the first thing that the procedure tells you to do is effectively just what I call charging your solvent, meaning that you add either an acid or a base. In this case, it's a base, so you are making it into a more basic solution using sodium bicarbonate. And so the reason this is important, and the reason you want to make your solution basic, is really for two reasons. One will be more beneficial towards the workup, but the other is that, remember that I said that the pKa of an amine in this case is probably around 8, and if you know anything about amino acids, in pH 7, they're typically protonated at the amine, okay? And so that's important because if I'm trying to do a nucleophilic addition onto an acyl chloride, I'm going to have a free lone pair. And if I don't have a free lone pair because the amine is and I'm just drawing over this, but if it's pre-protonated, there's no reaction. So I would drop down I would increase the basicity and increase the pH to ensure that what I call is free basing your amine. So you free base your amine to make it have a free lone pair, and then you can ensure that you actually can have a reaction that goes to completion. For extra information, this is called 6-APA, which means 6-aminopenicillic acid. You don't really need to know that, but what you do need to know is that this guy is pretty important right here. And that what we're going to be doing after this is recognizing what is and isn't the limiting reagent and excess reagent, because this will have to be beneficial for us during our workup procedure to see what we want to remove and how much of it we have to remove and what to expect on a TLC. So I'm just going to flat out tell you that the acyl chloride is the excess reagent, and your 6-APA is going to be your limiting reagent. So your excess reagent is excess by 2 times, and I also want to note something. You're using a lot of potassium bicarbonate. I think it's either potassium or sodium bicarbonate, but you're using a lot of base, and you're using a lot of base for a specific reason. 1, you have this guy to deal with, and 2, your base is probably first going to depronate the carboxylic acid because it's more acidic than a protonated amine, as opposed to this guy right here. So that's the important component. That's why you actually use a lot of base, okay? And this is something you should consider in any synthetic strategies, like how many acid base sites do I have, and so how much base should I use? And if you look at it, you're using like 1 gram of sodium bicarb, which is actually a lot. I did the calculations myself. It's about 0.1 mole of bicarb compared to 0.0025 mole of APA and 0.005 mole of acyl chloride. So that's why you use such excess amount of bicarb. But what happens is that once you add that bicarb, you want to now add your 6-APA. And this is basically just ensuring, and the sequence, in my opinion, matters. And the reason it matters is because what can happen is that, okay, if I add my 6-APA and wait a little bit, a neutralization reaction can occur where your OH gets deprotonated, and then after that, sequentially, effectively, your amine gets deprotonated. This just helps your reaction kinetics, because if I were to add both the acyl chloride and the 6-APA at the same time, I would have to wait for my limiting reagent to get freebased before I can do a reaction. Whereas if I have it already freebased and I just add everything, well, everything being just the acyl chloride afterwards, the reaction is ready to go. Also, more importantly, the reason I don't add the acyl chloride in before I add my 6-APA is for another reason. The acyl chloride is also an activated carboxylic acid derivative, and it means that it's prone to hydrolysis, unfortunately. And so in order to ensure that my excess reagent isn't going to get used up prematurely as well, I want to add my limiting reagent in first that is a little bit less prone to hydrolysis. It's still kind of prone. I mean, amides are typically more inert to hydrolysis compared to acyl chlorides, but the 4-membered ring component of it could be an issue. And this is just something that you're going to have to deal with. There's going to be a little bit of possibly amide hydrolysis right here. And there's also going to be a little bit of acyl chloride hydrolysis. But that's why we made the acyl chloride an excess reagent. So then we can ensure that even if some of it gets hydrolyzed, we still have more to continue our reaction. So let's say the reaction does go, and the neutralization reaction happens. You have the 6-APA, it gets freebase, and then you want to add your acyl chloride. It says in the directions to add it at a drop of 1 drop per 5 seconds and stir at that time. The reason this is important is because the reaction is possibly exothermic. And to ensure that your reaction doesn't overheat all of a sudden, you want to do a sequential addition of some reagent that would ensure that it would heat up a little bit and then it would drop back down in temperature. This way, 1, too much heat can cause other reactions to happen. So let's say you're trying to control kinetics. But also, too much heat could possibly degrade your compounds. This is a hypothetical, by the way. It's not necessarily for this case, but this is why sequential addition of reagents is done as a form of control, a kinetic control. And so basically then you just wait for the reaction to occur, and you can now begin the workup after 40 minutes, assuming you've TLC'd and everything and you've seen that your reaction has gone to completion. So the reason that I said also that making the solution basic is a relatively important component is for the following reason. Typically, most reactions aren't perfect, so what is realistically going to happen is you're going to have two things, or a few things in your reaction mixture. And I would highly recommend, whenever you do a reaction, to say, okay, what do I have in the start, and what is the pH of my solution at the start, and everything that's inside there, including the solvent. And then additionally, when I finish my reaction, what is everything that is possibly in my solution, plus the pH of that solution as well, okay? And that's super important. So to simply just list them out, assuming that, the acyl chloride is your excess reagent, you're still going to have acyl chloride remaining. I've also done a little bit of looking into what the acyl chlorides are. They're more non-polar acyl chlorides. Take my word for it. They're really just benzoic derivatives for the R group. You're going to have your acyl chloride. You're going to have H2O and acetone as your solvent. And you're also going to have, assuming your reaction didn't go to absolute completion, which is typically the case, especially in a class like this where you're shorter on time, you're going to have some limiting reagent. And you're going to have your product. And all your product is a more non-polar derivative of the 6-APA. Okay? But, so let's just say D6-APA for a derivative of 6-APA. And there's possibly some impurity, some hydrolysis of your beta-lactam, okay? This is like question mark, and really this is also question mark. It just depends on how lucky you are and how much of this is an issue. But this is a worst case scenario, effectively. And so immediately, I can tell you the following. You have to figure out what the pH is. And the pH is pretty basic, so it's above 7. And so what that really means is that this carboxylic acid is not going to be a carboxylic acid, but rather a carboxylate salt, okay? So this guy right here and this guy right here are actually pretty soluble in water right now because of the fact that the carboxylic acid is deprotonated, okay? Again, water and acetone, don't worry about that, but your acyl chloride, the excess reagent, is still also in your solution, and that itself is going to be nonpolar, okay? Just from the things that have been listed. So, if I know that these two guys are soluble in my aqueous, because they're salts, and my acyl chloride is actually nonpolar, I have water and acetone, so effectively I just have a mixed polarity solvent, and I have an impurity, and that impurity, by the way, is just going to have this guy cleaved right here. So what you would really see is a pretty soluble salt as well, because what you'll see is that if this guy hydrolyzes at this point, you'll have this. R being this guy right here. So R, and then kind of boom, boom, and an amine. Okay? So again, this is actually going to also be deprotonated at the carboxylic acid for your impurity again. So this is completely hypothetical, but it's always good to think of impurities that could happen in your reaction. But this is everything that you have. And so now you're going to go towards the workup. And this is a pretty elegant workup. That means that you basically only just do a bunch of extractions, and you should ideally get a pure product by doing them correctly. And so what you do is you get room temperature, and I believe what the actual compound is N-butyl acetate. Okay, so what it is it's a nonpolar compound. And what it'll do is obviously create a partition. And the diagram provided in your pre-lab is pretty good, but I just wanted to point out to you that this is why everything is moving in the appropriate spot. So, and this is why, by the way, you do this step first and not the next step for the workup, which is acidification of your compound. Okay? Because what happens if I add my N-butyl acetate first with my basic solution, I can actually extract my acyl chloride. So my acyl chloride will move into my, assuming, by the way, this is the top layer. I don't know the densities of this, but assuming this is the nonpolar and this is the aqueous, I'm going to have all my impurity, limiting reagent, and my derivatized 6-APA all into the aqueous layer. And obviously the H2O and acetone will partition appropriately as well. So acetone will go into the nonpolar, H2O will pull down. And you do this 2 times to really ensure that you've pulled off your acyl chloride and you just combine your aqueous, okay? And I hope this makes sense why everything is moving into the aqueous layer except the acyl chloride, because these guys are salts. Again, to reiterate, your carboxylic acid is deprotonated below like any pH that is basic, okay? Or above any pH that's basic. So you have these salts, and you're going to just drain and get your aqueous layer, okay? Once you have your aqueous layer, what you're going to do next, or the next thing to do from here, is to acidify. Because right now you're basic, so everything is going to be soluble in water. But if I were to acidify it, I'm basically removing a charge from my molecule, making it more nonpolar. And this is where I can use a little bit of the acid chemistry to come to my benefit. So when I acidify it, and by the way, just a helpful recommendation, always write out what you have after the first workup procedure. So what's remaining right now is my limiting reagent, so just the 6-APA. The derivatization of it, derivative, pretty sure I spelled that wrong, and the impurity, which is really just a carboxylic acid with an amine. Okay? And what I'm going to do is I'm going to acidify to pH 2. And this is important because you don't want to go to like pH 5 or pH like 6, even though they're acidic. You really want to ensure that like all of your carboxylic acid is fully protonated. So if I go to pH 4, there's, some carboxylic acid that's still, deprotonated. So you really want to push it past. But you don't want to go too far. And the reason I also say you don't want to go too far is that in your workup procedures, sometimes, if you're not quick enough, you can also start catalyzing hydrolysis. And what I mean by that is, again, you have this beta-lactam group, okay? And so if I drop this to pH 1 and let my thing sit in there, there's a great chance that I could do acid catalysis of this amide and do a hydrolysis reaction. So again, you have to be cognizant of the pH. Like going to pH 2 is specifically used to ensure your carboxylic acid is protonated, okay? But you don't want to go so acidic that you start catalyzing a reaction that is unfavorable, and that would start driving to get more impurity, okay, from your derivative, okay? So you have to be very cognizant of the pH. And what's more important here is that you have to recognize what type of acid you're using. You're using 6 molar sulfuric acid. 6 molar sulfuric acid contains 60% water, I think, which means that, you're going to have water in your solution. So hydrolysis is definitely possible, okay? And that's why it says cautiously acidify to pH 2, but also because it's just a safety concern. And what the interesting component of this is that it's cold N-butyl acetate. There's 2 reasons why you want it to be cold. One, to manage kinetics, right? You want to ensure that you don't get hydrolysis. So if I drop the temperature, the odds of hydrolysis to happen on my derivative that hasn't, deformed is lower, right? As opposed to doing it at room temperature, which we did in the first workup. Secondly, and this is a typical lab procedure, whenever you use acid and you want to acidify something, you really want to make sure that you have whatever your reagents are in an ice bath, okay? The reason that's important is because the neutralization reaction with acid can create heat, and so you want to sequester that heat. You want to make sure that especially if your compounds are heat sensitive, you want to ensure that you can sequester the heat because it's an exothermic reaction. So, as mentioned here, you place the aqueous solution in the 50 ml beaker and you put cold N-butyl acetate, and then you also put it into an ice bath. So you're really ensuring that you can prevent hydrolysis, prevent exothermic reactions from really damaging your compound. Again, this is all safe precautions. And what I would highly recommend is waiting about 5 minutes and then rechecking the pH to see if you've actually dropped to pH 2, because sometimes you have to wait for an equilibration to happen. If you go past, or if you manage to go above pH 2, re-add, stir a little bit, and check again. But then what happened here is the next thing that's pretty important, is to recognize the transformations that are taking place. Remember, you're protonating your carboxylic acid, but what else are you doing? Well, there's a few things to recognize. I have just shown here the 6-APA molecule, the starting material, right? Your limiting reagent. So if I'm acidifying to pH 2, not only am I getting this carboxylic acid, but I'm going to be protonating this amine. Absolutely protonating. Super acidic of a solution, and the amine is a great base. So I make the limiting reagent soluble in my aqueous layer. I would also be making, and so I'm just going to draw this here. This goes into the aqueous layer because the amine also gets protonated, amine plus, My impurity, which I drew out for you, kind of has this structure. It's not exactly what the 6PA, the actual impurity looks like, but just this, it has this structure. It also has an amine that will get protonated. So that will move into my aqueous layer. But like I told you, that what I'm adding for my R group or with my acyl chloride, whatever this R is, it's a non-polar R group, okay? It's typically a benzene ring that you're adding. Things that are not really having acid-base behavior. And so this guy, although it's carboxylic acid, will get protonated, making it more nonpolar. It will also just be more inert to this acidic condition, and so it can move up into the N-butyl acetate layer. And then what you do is just and I'll just draw this here, you're going to get this into the organic, and obviously you have to do a little bit of shaking and moving, but yes, ideally you're going to get this into the organic layer. So then from there, and I'm just going to read it off, is that you basically just put this into a vial, and then you just do several washes with water to make sure that you remove the acidity. And also I'd recommend doing a brine wash, but also after that you're going to put a drying agent. In this case it is sodium sulfate, and ideally that can remove the water. The reason that's important though, removing the water, is for the next step, which is your crystallization. Okay, your crystallization of your compound, or of the 6-APA. And effectively, the reason you don't want water is because what you're adding to your filtrate, which is just your compound, which is, by the way, a nonpolar substance, and at this point, because it's in a nonpolar compound with no acid bases, it's just a neutral molecule that's relatively more nonpolar, meaning it's soluble in this. You're going to add a 50% solution of potassium 2-ethyl hexanoate in butanol. So butanol being a organic solvent, you're adding a little bit of base to it, soluble base. What that does again is taking advantage of this carboxylic acid group and making it into a potassium salt. The reason that's important though is because if you make this into a potassium salt, you're making it a charged molecule, and then it would want to crash out because it doesn't want to be in a non-polar environment. Especially, butanol is like got one hydrogen bond donor, right? And acceptor being the OH group. But at the same time, to be perfectly honest, it's relatively more nonpolar. Nonpolar enough, I'd say, and so would the pre-lab, say that it's enough for it to crash out. You can also facilitate that crashing out by reducing its solubility using an ice bath. But this is important to recognize why the procedure says make sure that your compound is not wet. Because if you had wet compound, right, what would happen is that it would just dissolve as a salt into the water, and you kind of get like a partitioned solution, and that would just make your life much more difficult to kind of extract and then re-put in and re-dry, right? So if you just make sure that whatever you're putting into the butanol is dry, right, your isolated 6-APA, and then making it into a salt, it would be much more easier to have that dry before, it would be much more easier to have that dry as opposed to adding it as a wet solution, which would then be partitioned into the aqueous layer, and you'd have to redo everything effectively, redo the final step of drying. And again, the dryness is obviously kind of emphasized here because it says use dry acetone, and that's really it for the most part. What I would recommend also to recognize is that you should probably characterize your starting material and also your final product. This obviously is part of the post lab, but just the importance of that is to make sure that you don't have any starting material in your final product to really ensure that you had a successful purification process. But otherwise, that's the entirety of this procedure for the synthetic component of it. I think I did a pretty clear job at doing this. If not, ask me questions. See ya. Good luck.